Yes, sir.
So from infinity, you will come closer.
Mm.
The lens is here. Okay. So this is the principal
Mm.
axis.
Mm.
First, I'll keep the object very, very far away. Object.
Okay.
Okay. The focus is somewhere here. F1.
Uh.
I can also make the double the 2F1, one marking.
Mm.
Similarly, on this side will be F2,
Mm.
2F2. What is biconvex? Convex lenses F1 and F2 will be same. Actually, F1 and F2
Okay.
always same. Okay.
Mm.
So next one is I bring the object closer. So
Mm.
this is called center of curvature. This is the focal
Mm.
point. Okay. So next
Mm.
is the object is between the outside. Beyond C, that's greater than 2F. So next the object is here. This is the first one. This is the object in second case. Okay.
Mm.
Once I have this thing, uh, beyond 2F. So this is F1, this is 2F1. So this is the object I represent by a stick, AB. B is the top of the stick. Okay. So I can use the rule here. Take two light rays starting from this top point. One is this one, which
Mm.
is parallel to the principal axis. So the rule says after the refraction will pass to the focus. Okay, I'll go straight.
Mm.
Second rule is the one which is passing the middle point, that's optic center will go undeflected.
Mm.
Okay. Now I can also
Mm.
use the two lines are enough. If you use the third one, the one which is passing the
Okay.
this
Mm.
refraction
Mm.
will go parallel to the principal axis.
Ah.
So that also will come and meet
Ah.
at the same point.
Mm.
But to find the intersecting point of end lines, okay, if I find intersecting of two lines, that'll give me the point.
Mm.
Correct? No.
Mm.
So
Yes,
intersect.
sir.
Say there are 10 lines. To find this point, I just have to take any two lines and find the intersection. Okay. So from this point, there are infinite light rays coming out. There is one more light ray coming here, one more here, one more here. But I'm taking these two special rays. This also a special ray. But even if I take this in between arbitrary ray, after refraction will pass through here only. There is no proof, but you have to accept it.
Mm.
Okay. So
Mm.
even a light ray like this, after
Mm.
passing the lens, will come and meet here at the same point A. So all the light coming out from A will come and meet at
Mm.
A, and they call it A prime. Because A
Okay,
prime is
sir.
image of A. Okay. But just two rays are enough. The two rays
Mm.
we are taking this one is parallel to the principal axis. Here is
Ah.
the ray. After refraction, will go through the
Mm.
focus, and second is passing the center, will go straight. So those two intersect with
Mm.
some. There is a place where the image of A is formed, it's A prime. Similarly, I take two rays from B. One is through the optical center
Mm.
straight. Okay.
Mm.
And
Mm.
the second one, you want to take the second one. What you can do is you can take a middle point,
Mm.
say C. Okay. And do the same thing.
Okay.
One parallel to the principal axis.
Mm.
You apply the same rule. We pass through this focus and go like this. Another one from here, pass through the center, go
Mm.
undetected and come and meet here. So image of C, it's
Mm.
C prime here. So if you look at this portion AC, it's getting inverted as
Mm.
A prime C prime. It's getting inverted, no?
Yes, sir.
Um, B is a limiting case. It's difficult to figure out. So
Ah.
you can take a very, very uh, small point, close point to B. Say B,
Okay.
say B1.
Mm.
Then you can figure out that image of B1 is here.
Mm. Mm.
Okay. So this is the, so this,
Mm.
this thing will come.
Okay, sir.
So the image will be real and inverted. Inverted, I just showed why it's inverted.
Mm.
And size of the image is merged.
Okay.
Okay, object at C.
Mm.
Again, you take it two rays. One is parallel to the principal axis. After fractional, go to the focus. Another is to the center,
Mm.
it will go undeflected. So this one.
Mm.
So this is the center of curvature, which is twice the focal length. So at this point,
Mm.
the object size and image size are same. Again, it's real and inverted. So
Mm.
basically, they're coming closer. See, first
Yes,
you're
sir.
next you're beyond the C. Third thing is here.
Mm.
Third image.
Mm.
Third object. Third case. Fourth case will be here between F and this one. Fifth case will be here at the focus. Sixth case will be within the focal length. Okay.
Okay, sir.
So second case is this one beyond C. Third case is at
Mm.
C.
Mm.
Fourth case is between F and C. So this is
Okay, sir.
and this is C. So same two rays, parallel to the will go here, pass to the focus, and this one, this one. So here you can see A prime. See, geometry, you just follow the rules and draw the lines, right? Similarly,
Mm.
if you follow the geometry and draw the lines, you can actually visibly see that this thing is bigger.
Yes, sir.
You just have to follow the geometry rules. So here you can see
Mm.
visibly that this thing is smaller, right, compared to this one.
Mm.
Here, if you follow the rules, here also you can see both are same size.
Mm.
Here you can see the size has become bigger. Just by applying
Mm.
geometry itself, we can get this result. Next is coming to the focus. So here it will pass through the focus in one. So this will be parallel beam of rays.
Mm.
Okay, this will never meet. Next one is within the focal point, between the
Mm.
center of focus. So here, if it goes here, we'll go through the
Mm.
parallel beam.
Mm.
They showed it wrongly.
Mm.
Use F2. Okay.
Mm.
Parallel beam will, after this thing, will go to the focus. And one of this part
Okay.
will go straight. So this thing is getting diverted. There's a divergent rays. Here, if you look here, these two are converging. The distance is decreasing, right?
Mm.
Here it's converging.
Yes.
Here also it's converging.
Ah.
Also converging. Next one is becoming parallel. Okay.
Ah.
After parallel is a little
Mm.
diverge.
Okay.
What is happening constantly is you are getting closer and closer.
Mm.
First year here, you are getting converging rays here. Second here also converging.
Mm.
So up to here is converging rays, the one which is
Mm.
coming. Okay.
Mm.
At this point, when it's at the focus, it will become parallel. Okay.
Mm.
Here it will become
Mm.
divergent. Okay, between object and the focal point, the object is here, between the lens and the focal point. So here the outcoming rays are divergent. So now it will not meet, but if you
Mm.
uh, project it backwards, it will meet somewhere.
Mm.
So this is
Mm.
like a virtual image.
Okay.
It's not a real image.
Okay.
But the image size will be larger.
Okay.
Large.
The converting images, sir?
No, erect image.
Okay.
All these refracted images are inverted.
Mm.
Okay. Here image will not form, but here it's a
Mm.
virtual image, but it's enlarged.
Okay.
So convex lens it's used for camera lens because usually camera
Mm.
the object is like a distance. So the light coming up from the
Okay.
object will get focused at a particular point in the screen of
Mm.
the lens. Okay.
Okay, sir.
Use of magnifying lens because in certain cases the image size is bigger than the object size.
Mm.
Microscope and projector and also for eye specs.
Mm.
So that's all. We covered all the cases. Once you get closer, start
Mm.
from infinity, parallel beam of light will come. Here, the object size
Mm.
is lesser than the image size. Here, it's equal. Okay. After that, the
Mm.
image is enlarged. Here, you won't form the image. It's parallel beam. After that, it's virtual image enlarged. So you covered the full range, starting from infinity. Object in infinity.
Mm.
Okay, beyond C,
Mm.
and then between F and C, and then
Mm.
at F, and then between F and the center. So full range is covered. So beyond focal point, there'll be really real image. At the focal point, you are getting the parallel rays, and within the focal
Mm.
point, it's divergent rays, so it's having a virtual image.
Mm.
Concave lens, its number of cases less because whenever it's so far away, it's parallel beam, it will produce divergent rays. So form a
Okay.
point image at the focus. When you come
Mm.
closer, wherever it is, it will always produce divergent rays. So you have to project
Mm.
it backwards and get a erect image here. So this is the object. This thing is A prime B prime,
Mm.
and it's erect, but it's
Mm.
virtual image
Mm.
because
Mm.
this thing is got by projecting the light rays
Ah.
backwards. So this is not a real light ray.
Mm.
So object anywhere between on the principal axis at finite distance.
Ah.
This will become a point image. Otherwise, it
Mm.
becomes smaller image. So if you keep moving this thing far and far away, this thing will become smaller and smaller. When this thing is pushed to infinity,
Mm.
this small thing will become a point,
Mm.
like this case, object at infinity.
Okay, sir.
Here. So 1, 2, 3 is coming nearer and nearer and nearer. So
Mm.
magnification is decreasing or increasing.
Mm.
So
Mm.
as they come closer, its image size is getting increased.
Mm.
So the magnification formula will be like
Mm.
V by
Mm. Mm.
magnification will be
Okay.
V by U. So as you come
Mm.
closer, V is decreasing.
Mm.
So magnification will go down.
Mm.
Hmm. And also U is also changing, no? So it's not obvious.
Ah.
V is also
Okay.
changing. Okay. So V is
Ah.
decreasing, but also
Mm.
U is decreasing much more than that. So that magnification
Mm.
increases.
Mm.
Concave lens.
Mm. Mm.
Right. Okay. So in this thing, there are only two cases. One is
Okay, sir.
within the focal point, they have not discussed.
Mm.
One is at infinity. Second case
Mm.
is when it's even within the focal length, this result is same, I think. Here,
Mm.
the fifth case is within the focal length. Okay, so all
Mm.
these cases, the result is the same. It's virtual and erect.
Mm. Mm.
In the infinite case, again it's a virtual and erect, but it becomes a point image.
Point image. Okay.
This thing becomes smaller and smaller as you go far away. It will become a point when it's
Mm.
infinite. Like here,
Okay.
as you go far away, means it's becoming one, right? So it's becoming smaller and smaller.
Ah. So the image will be greater, no, sir?
As you come closer,
Oh, okay.
image size will increase. So
Okay.
infinity, the image size is a point size.
Hmm.
So you can use the image distance, sorry, object
Mm.
distance. This is the object.
Mm.
So this much is
Mm.
U from the center,
Mm.
and this is V, image distance.
Okay.
But one important thing is this distance with the
Mm.
sign. You have to put the sign. See, in the
Hmm.
x-axis, there is 0, right? There is 1. There is
Huh.
minus 1,
Huh.
minus 2. So suppose the thing is here, then this u is minus
Hmm.
1.
-2.
So u we
Okay.
can remember as object distance with the sign
Hmm.
or coordinate of the object.
Hmm.
Okay. So 1 by u plus 1 by v. So to remember this formula,
Hmm.
the general easy case is convex lens.
Hmm.
Convex lens. So the object is somewhere here. The image will be
Hmm.
inverted and like this, right? And
Hmm.
this is the center. So this is the origin of the x-axis. Okay. And
Hmm.
direction, positive direction of the x-axis is the object is here, the instant light direction is towards right. So the positive direction is towards right.
Hmm.
Okay. So the formula is 1 by u plus 1 by v equal to
Hmm.
1 by f. But all the terms should be positive. U is negative here because of the left side. So to make it positive, put a
Okay.
sign with this one. And U is positive in this normal
Hmm.
case. So it's this one. And the focal point is here.
Hmm. Hmm.
So there's a focal length. That's also positive. So that's why the minus sign is the U.
Hmm.
You can remember this formula. 1 by
Hmm.
1 by U plus 1 by V, but I have put the minus sign with this U to make it positive.
Okay.
So this is the lens formula. Sign convention I just said. Direction of the instant light is positive. Origin, basically, I would choose the origin in that positive direction. For x-axis, origin has to be fixed, which is
Hmm.
the center of this lens.
Hmm.
And one direction is positive. This is the instant light. This is the object.
Hmm.
So the light ray will come like this. So this is the positive direction.
Okay. Hmm.
Similarly, for measuring the height of the
Hmm.
object or the size of the object, I have to measure in the perpendicular
Hmm.
direction.
Hmm.
Because I have to measure this height of this object as h. Then this is y-axis. Origin of the y-axis is this one only. But the positive direction is upwards.
Hmm.
Okay. So this height is positive. This h
Okay.
prime height of the image is negative because
Hmm.
it's inverted.
Hmm.
The sign convention for both x-axis and y-axis. Distance measured upward or positive. Magnification is the obviously the image size
Hmm.
by object size.
Hmm.
Magnification is image size h prime by h.
Hmm.
And it's v by u.
Hmm.
And lens makers from see lens will have a
Hmm.
focal length, right? Now, in general, the lens, the curvature of this surface can be R1
Hmm.
and this surface can be R2. What is biconvex means both R1 and R2 are same, but it's not necessary
Hmm.
for it to be same. It's R1 and R2 in general. So
Hmm.
if the thing is more curved means it is a smaller sphere. Okay. Then the bending will be more. So basically the focal length depends on this R1 and R2. And the relation is 1
Okay.
by R1 minus 1 by R2 into mu minus 1. It depends on this
Hmm.
refractiveness of this material also. So 1 by F
Hmm.
is mu minus 1 into 1 by R1 minus 1 by R2. Again, you have to choose one direction as positive. Okay. So this R1
Hmm.
is positive because on the right side. This is the origin. R2, the center is here.
Hmm.
So R2 is negative. So this become a positive
Hmm.
quantity with the if you include with the sign. Because R2 is negative. So when I use this negative sign, this thing will become negative positive. So both these things will add up.
Hmm.
Take a special case of this
Hmm.
biconvex with R1 equal to R2.
Hmm.
Actually, magnitude of R2. Magnitude is same,
Hmm.
but suppose R1 is say
Hmm.
5 centimeter, R2 is
Okay.
minus 5. because on the left side.
Okay.
This is my origin, this positive source, right? Okay, so
Mm.
you put 1 by 5 and minus 1 by 5 will become plus 1 by 5 because of minus sign here.
Mm.
So that way you can figure out this minus sign is required.
Okay.
Otherwise, you get the wrong answer. Mu minus 1, mu is around
Mm.
1.5, 1.5 minus 1 is 0.5.
Mm.
So the person who is making the lens, he has a choice of choosing this.
Mm.
You can choose a sphere of small size, or you can choose a sphere of bigger size. What is the difference between these two spheres? The difference R1, this is different R1. Okay, so depending on what choice I choose, I can adjust this value of f.
Mm.
That's what the lens maker will do. The person who he will say, I want lens of focal length 50 centimeter.
Oh.
Okay,
Mm.
he will choose some R1 and R2, so that it gives the focal length of
Mm.
50 centimeter.
Mm.
So that the designer lens maker will decide. The maker of the lens will
Mm.
decide what should be R1 and R2. He'll be given the job of say f should be 50, and he will decide what should be R1 and R2 to give me 50. That's why it's called lens maker's formula. The
Okay.
maker of the lens will use this relation
Ah. Ah.
because what he'll have is 50. To get the 50, what should be R1 and R2? Suppose he's designing biconvex and both R1 and R2 are same, so it will be 2 by R
Mm.
into mu minus 1 is
Mm.
say 0.5. That should be equal
Mm.
to 1 by f, which is 1 by 0.5.
R. Okay.
Why did I put 0.5? 50 centimeters, right? I put 0.5.
Ah.
Why?
Yeah. Because we are converting it, right?
Yeah, SI units.
Ah. Okay, sir.
SI unit is 0.5 meter. Okay, so
Mm.
1 by 0.5.
Mm.
1 by 0.5 is same as 2, so this and this will get cancelled. Okay, so
Mm.
R is 0.5 meter. That is 50 centimeter. Okay, so for biconvex lens of focal length 50 centimeter, R should be 50 centimeters
Mm.
for refractive index of glass being 1.5.
Okay, sir. Ah.
The lens maker will choose two spheres of radius 50 centimeter,
Okay.
make the lens.
Mm.
And power of the lens is, see, the job of the lens is to bend the light.
Ah.
See, the lens is not there, the light will go straight.
Mm.
What is happening? Wait, wait, wait. If lens is not there, the lighting will get straight. But suppose lens is there, you'll bend like this. Okay. But I can change the lens and make it bend more. Okay. So bending is more means the lens is more powerful. Here in this case, the focal length is f1. Here the focal length is f2. Which f1 is more or f2 is more? F1 is more. If the bending is less, you'll go and hit the principal axis at a faraway point, right? If the bending is more, you hit closer. Got it now?
Yes, sir.
Huh. So what I'm saying is lens is more powerful if f is
Mm.
less. Okay.
Ah.
So to get the idea of power of the lens, I'll do 1 by f.
Okay, sir.
So if f is small means power is more. That's how the reciprocal relation.
Mm.
Understood now?
Ah, yes, sir.
So
But
small
the
f means
last topic I didn't understand.
no. See, job of the lens is to bend the light. Okay.
Okay.
So if the bending is like this, then it'll go and hit this thing here, right? So this much is the focal
Mm.
length. If the bending is
Mm.
more, it'll go and hit here. So this is the focal length.
Mm.
So if the length is
Mm.
different. Okay. So what I'm saying is if F is less means power is more.
Mm. Mm.
So that means it's an inverse relation, right, between power and focal length.
Yes, sir.
Okay. If you have this relation, that means when F is more, power is less. When F is less means power
Okay.
is more. When F is less means bending is more. So lens is more powerful. Job of the lens is to bend the light. If the amount of bending is small, you'll go and meet far away, right? If the light is not bending, it will never meet. But if the at this point the bending is slight,
Huh?
if the bending is slight like this at this point, it'll go and meet
Okay.
the principal axis somewhere here. But if the bending is more, it'll go and meet here
Mm.
itself.
Yes, sir.
So this is the lens. So obviously
Mm.
the focal length less means lens is powerful.
Mm.
Okay,
Mm.
that's why the relation is inverse.
Mm.
Power is 1 by f.
Mm.